Okay, so hello everyone. I'm excited to advertise our latest research on J1, J2 fractals by the method called Multi-Recursion HOTRG. And for those of you who are interested, you can look at our preprint, which is already on arXiv. And this was actually work in collaboration with Jozef Genzor from Slovak Academy of Sciences and Ingjir Kao from NTU. And the main motivation or main question of this work is to study what happens with the phase transition phenomena as we transform a square lattice of some non-integer dimension into a regular lattice, like a square lattice. So in this case, we have a fractal lattice with Hausdorff dimension, which is 1.792 approximately, and we want to transform somehow this lattice continuously into the case where this dimension is equal to 2. Just the refresher on fractal dimensions. So fractal dimension or dimension can be understood as an answer to the question, what happens to the system as we...
Joseph, I have a question.
Yep.
We can see your title page. Is it okay? We haven't seen the next. Are you showing the next slides?
I'm now showing the slide with fractal dimensions.
You are speaking upon the title page.
Oh, no, I switched to the next slide.
Oh, no. We are seeing title page only. Okay, this is okay.
Oh, that's strange. Okay. Okay, now, yeah. Thank you very much, Tomotoshi. So let's move on to next slide. So the Hausdorff dimension will deal with the scaling of the volume size with the system diameter, right? So this definition basically says that the volume size increases as a magnification factor to the power of Hausdorff dimension. And we might define the dimension also from another angle, and we can look at the scaling of the boundary size with respect to the diameter. In the case of lattices, the boundary size can be counted as the number of outgoing bonds. And here, this definition says that this boundary size scales as the diameter to d minus 1, where d is this boundary dimension, right? And then we can think which of these two dimensions might be important depending on a particular case. Let me now show you this fractal lattice. So I call this fractal Nishino fractal because the first time I saw it from Tomotoshi Nishino during a visit of Japan in 2015. And later we made some calculations for our study of phase transitions on this fractal. And here we depict basically the composition of this lattice. So we start from some basic unit cell, and then you would arrange this basic unit cell according to some prescribed pattern. So in this case, you would take 12 copies and you would arrange them in this 4x4 regular square lattice with 4 corners missing. And we would repeat this procedure iteratively until we reach some desired system size. So at each step, a number of sides of this lattice would increase by a factor of 12. And therefore, the Hausdorff dimension would be approximately 1.792. And also, at each step, number of outgoing bonds will get increased by a factor of 2, which gives us this boundary dimension to be exactly 1.5. And also, we can, in a similar manner, define extension or composition of this kind of fractal. So this is a Sierpinski carpet. Interestingly, the Hausdorff dimension is the same as in the previous case. However, the boundary dimension is equal to exactly 2. And we can even talk about some other, let's say, more interesting or strange lattices, like this labyrinth fractal. And this labyrinth fractal has the boundary dimension equal to 1. All right, so let us now jump straight into the J1, J2 fractals. So we would simply introduce another type of coupling. So apart from these thick black bonds, which would represent the J1 couplings, we'd also have the couplings which were previously missing on the square lattice frame. And these would be J2 couplings, denoted by thin bonds in red. And we basically, when we set J2 equal to 0, we would obtain a pure fractal lattice. And when J1 is equal to J2, we would obtain a regular square lattice. Right, so this would be third iteration of this extension procedure. And similarly, we can also define or construct in this way a J1, J2 Sierpinski carpet, or even this exotic J1, J2 labyrinth fractal. And just to avoid any confusion, we want to study the phase transition phenomena of classical Ising model on this kind of continuous family of fractal lattices, where the Ising spins are located in the sides of the lattice and are interacting, like the nearest neighbors are interacting either with the coupling J1 or J2. Okay, so what is already known? So this was our previous research using HOTRG on this Nishino fractal. And, oh, sorry. And what we found was that, first of all, HOTRG works reliably on this fractal. And we are able to obtain order parameter. And from that, we extracted critical temperature and critical magnetic exponent beta. And we showed that this magnetic exponent beta is roughly 1 order of magnitude smaller than that on regular square lattice. Moreover, there is another difference when comparing with the regular square lattice, and that is that there is no singularity at the peak of the specific heat. However, there is a weak singularity at the critical temperature. So this corresponds to inflection point of the specific heat. So we perform the first derivative of the specific heat with respect to temperature, you would get the divergence at Tc. So that's like a new behavior found for this fractal lattice. Okay, so let me now show you some numerical results for this new technique on J1, J2, J1, J2 fractal. So first of all, we should compare how does this method deal with the extreme values. So when J2 is equal to, or first of all, we would fix J1 to be equal to 1. And what we want to do is to tune only the parameter J2. Right, so when J2 is equal to 0, we have a pure fractal lattice, and we can compare our new results with the previous ones, and there is excellent agreement in critical temperature. And also this estimation of critical temperature is actually very reliable and does not really change as we increase the bond dimension above 16. And also for the square lattice case, when J2 is equal to 1, there is also very good agreement with the exact solution. So for moving on to critical exponent beta, we see that our new results, again, are consistent with previous results. It's difficult to say which ones are actually more accurate. There is a relative difference at around 10%. And for the square lattice, there is even better agreement. So this is some kind of sanity check that this method would actually give the expected results when we are in both of these extreme points. And so this is a fitting of magnetization in that case of pure fractal when J2 is equal to 0. And here, let me just remark that we place the impurity tensors only on the black structure. So only on the sites which are connected by the J1 couplings. Okay, and we could also extract the field response critical exponent delta. So this exponent delta again exhibits a good agreement with previous results, although before we used rather small bond dimension. So there is a reference to paper in Acta Physica, and good precision for square lattice case. So, but what is more interesting, of course, is what's happening in between these two regimes. We see that, for example, critical temperature slowly increases from the critical temperature for the fractal case all the way up to the exact critical temperature for square lattice case when J2 is equal to 1. And here we also plot some preliminary results for the Sierpinski carpet. So it also increases, the critical temperature also increases. However, it didn't find in the literature estimation of this critical temperature for a pure 4x4 Sierpinski carpet, so couldn't compare this. And so what happens with the critical exponents? So now we know that the critical temperature continuously increases But what about the character of the phase transition, and which is captured by exponents? So in the case of the beta exponent, beta does not change on the entire interval from 0 to 1, and it keeps to be the same as for the pure fractal case. And then there is a sudden jump to the correct value for the square lattice. So this is 1 order of magnitude jump at J2 equal to 1. So that is kind of surprising behavior. And we can also look at at the convergence to verify that this is indeed correct behavior which we found. So let us go very close to the square lattice case. So when J2 is equal to 0.99, and we see that these data points, which are obtained for the case when J2 is 0.99, are still much closer to the fractal exponent than to the square lattice exponent. And there is also good, very small difference actually between these values for d is equal to 32 and 34. So we have found similar behavior also for the delta exponent, where the delta exponent does not change on the entire interval from 0 to 1. And there is sudden discontinuous jump again by 1 order of magnitude at J2 equal to 1. So what about this anomalous specific heat, which we found in our previous study in the case of pure fractal? Well, this anomaly is also preserved all the way up to J2 equal to 1, where it transforms into square lattice. So we still have only a weak divergence of the specific heat for J2 less than 1 in the inflection point. So this specific heat actually is calculated as again as a local quantity, as a derivative of the internal energy with respect to temperature. And we can again look more closer towards the square lattice. And so when J2 is 0.99 or when we are above 1, so 1.01, we still see similar behavior, so only weak singularity. And the critical temperature corresponds to inflection point for the specific heat. So to further investigate the phase transition, we have also looked at the entanglement entropy in the case of J2 equal to 0.5. However, this is a representative case for also for other values of J2. So as long as J2 is less than 1, we observed this kind of behavior. And so the entanglement entropy can be calculated as a byproduct of SVD as we perform our HOTRG extensions, which actually I will show later, from the singular values of this SVD on local tensors. And we expect something to happen around the critical temperature. In this case, this should be around approximately 1.5777. So this would be entanglement entropy after one iteration or one extension. This is after second step, third, 4, 5, 6. And we already see that there are 2 peaks, which is kind of surprising.
Could you please show your slides? We can still, oh, okay, that's it.
Oh, sorry. So maybe you missed something. Okay, so this is from the initialization, and then we slowly extend the system and recalculate the entanglement entropy. So this is entanglement entropy with respect to temperature. And after 6 extensions, we obtain these 2 peaks. Where this peak on the right side actually corresponds or is located near the expected critical temperature, which was visible either from order parameter or specific heat. And this other peak we'll explain later, which is on the left. So as we continue, this looks maybe almost converged. However, there are still some small changes. And then entanglement entropy becomes a little bit unstable and collapses to this case with just a single peak. And it's converged from after 18 iterations. So it's interesting that there are 2 peaks. So let's first focus on the peak on the right side. And actually, there is some kind of fixed point, which corresponds, which is located exactly at the critical temperature. Oh, sorry. So this fixed point, the entanglement entropy does not change as we extend the system, and this captures the critical point even after a few steps of few iteration steps of this extension procedure. And this other peak, which is on the left, this peak actually is just a trivial phase transition which happens in the J2 regions, or these red regions, because this is just a shifted critical temperature of square lattice Ising model with decoupling J2 equal to 0.5, right? So so the only interesting thing is actually this this inflection point for the higher temperatures. And we can also look at what's happening when J2 is bigger than 1. So we call this regime inverse fractal. And we estimated critical exponent beta in this regime. It seems to be around 1/2. It's also stable with respect to the bond dimension. And as for the critical exponent beta, delta, or the field response critical exponent for the inverse fractal is around 5 or 5.1. There is just a small remark that when J2 is less than, when J1 is less than J2, then the J2 regions actually have larger critical temperature than those on the then larger than the critical temperature of the fractal. So this actually destroys the phase transition of the J1 structure due to some kind of external field acting at its boundaries. However, when J2 is not much larger than 1, we could still extract the critical behavior or properties of the inverse fractal. All right. Now I would like to talk about the method. A method which, as the title suggests, is based on multiple extension relations. So we have now multiple local tensors. So as in the HOTRG, we represent the partition function as a tensor network state. And here we would need 10 different tensor types of local tensors to represent such tensor network state. And each of these local tensors is extended by its own extension relation. So these relations specify how to combine the tensors of different types to extend a given tensor type. So for example, you can see that, for example, when we extend this tensor type 1, we would need 4 copies of tensor 1, 4 copies of this tensor type 10, which go into the corners, and then we would need tensors, 2 tensors of type 2, 3, 4, and 5, right? However, we would actually need all these extension relations also for other tensors, even though these tensors are tensors of other types, like, for example, 6, does not enter this extension relation for tensor of type 1. But we would need these other types to extend tensors like tensor type of 2, 3, 4, and so on. Okay, and this is actually not restricted only for this type of fractal lattice. This can also be applied for this 4x4 Sierpinski carpet. In this case, we would need 8 types of local tensors to represent the tensor network state. And each of them will again have its own extension pattern. And also, this idea is quite general, so we could even use this for extending the like this labyrinth fractal, but we would need 13 or 12, depending how you want to count, types of local tensors with some extensions. Right, so this seems to be easy to generalize to other types of lattices, especially when they exhibit some kind of self-similarity on every scale. Okay, so for the calculation, we perform HOTRG, which was introduced in this paper mentioned in the reference. And the partition function is evaluated by contracting the whole network. And this is done iteratively. So we perform some coarse graining steps. And here in the HOTRG on square lattice, which is translational invariant, we alternate between horizontal and vertical contractions. Right, so in this example, these 2 tensors are contracted along the y-axis, and we obtain a new larger tensor M with a larger bond dimension, which can be truncated back to some bond dimension cut D by obtaining these HOTRG isometries or projectors U. And then we would apply our projectors from both sides and obtain the projected tensor, projected and extended. So then this procedure will be repeated in the next step along the x-axis and so on. So our case is a little bit more complicated. because now we deal with these 4x4 clusters, and we want to contract 16 tensors, which comprise one unit cell. So here we would perform 4 steps of HOTRG style coarse graining by contracting neighboring pairs of tensors at each step. Okay, so this would be 1 step of HOTRG. After 2 steps, we have this 2x2 cluster, 3 steps and 4. And we just need to take care of properly matching the adjacent projectors. So for that, let me define firstly something which we call non-homogeneous projector patterns, and we will define those patterns on this on the extension pattern of the tensor type 1. Right, so you can see there are now not all tensors are of the same type. Now we just took the extension pattern of for the first tensor, and we calculate all these projectors, and some of them have to be the same in order to match these projectors properly. And so here we would obtain 15 different projectors. So then we would take these projectors and we might reapply them to other patterns where appropriate. And similarly, we'll define these homogeneous projector patterns. And here we have only 4 different projectors, because this is really just, so this is extension for the tensor type 10. So into this extension, only the same tensors are. So in this projection, we only need the tensors of the same type. Right. So then we would take these projectors and we might use them also somewhere else. So let's discuss the consistency of projectors. So the simplest idea would be to simply obtain the either homogeneous or non-homogeneous projectors, or any kind of projectors obtained from any pattern, and then just recycle them and apply them to other patterns. And this would satisfy the restriction that the projectors on the boundaries have to match. However, this is actually not very optimal approximation. So slightly better idea might be that we would recalculate the inside projectors of each unit cell separately. So these projectors, which we denoted as Aj up to Q, can be obtained separately for each unit cell, and that's fine, because they would not meet they don't have to be matched because they are not on the boundaries. But the projectors A, B, C up to F have to match other projectors because they might meet when we want to perform another next step of this extension, right? So we need to decide which projectors to apply at the boundaries. In our calculation, so this very simple solution, we just use 2 sets of internal projectors and 2 sets of external projectors. And of course, this is not the only way how to do that. There might be even better way, but this is actually simple, and it gave us numerically stable results. So let's talk about the external projectors on these 4 examples. And here we just use the external non-homogeneous projectors, which are denoted by black thick dashed lines, when truncating thick leg, these black legs, right? And these are obtained and optimized on this first pattern. And when we are truncating red leg, we would use the homogeneous projectors, which were obtained on this pattern. But because the red leg here is actually composed only of other red legs, so we see like this boundary is similar to this one, we might use this kind of approximation, and it works fine. So similarly for the remaining remaining legs. And the simple idea is also can be also used for internal projectors, and we would take the homogeneous, so non-homogeneous projectors, which are obtained from that first pattern, and we would just simply apply the same projectors also on the patterns from 1 to 9. And the homogeneous projectors are only applied in the case of the pattern 10. So here we use HOTRG style isometries. However, again, we might use, and it would be better to use actually maybe some boundary TRG or some other way how to obtain projectors. However, this was still sufficient in this case. So let me briefly summarize. So we defined a continuous family of planar self-similar lattices, which are constructed using two types of couplings, J1 and J2. And this allowed us to interpolate between pure fractal lattice and regular square lattice and study how the nature of phase transitions change as we perform this transformation. And our modified HOTRG approach employs multiple local tensors, with each of them being extended according to its own extension formula. So we found out that the critical temperature grows continuously as we increase the value of J2 from 0 to 1 by fixing J1 to be equal to 1. So it properly increases its value from pure fractal to square lattice case. However, the critical exponents beta and delta are more or less constant on the whole interval between 0 and 1. And this is followed by a sudden discontinuous jump at J2 equal to 1, where these square lattice values are recovered. And similarly, also the specific heat only exhibits a sharp singularity at the critical point in the case when J2 is equal to 1. And before that, we only observe a weak singularity in the specific heat at TC. So what we would like to consider next are also some other non-homogeneous lattices like Sierpinski carpet, which I also showed here. And we're also working on a 3D version and quantumizing model on this kind of continuous family of self-similar lattices. So thank you very much for your attention. There were some technical problems, so please ask me anything if you need me to show something again. So thank you very much.
Thank you. So is there any question? I have a question. Okubo-san first.
Thank you very much for your nice talk. Can I ask a question about the critical exponent? So based on your specific heat, I consider that the critical exponent alpha must be negative. And my question is it consistent with the scaling relation calculated from the beta and delta? So, so there is a relationship between the beta, delta, and the alpha, if we assume the scaling relation. And so probably we can calculate the alpha from beta and delta. And is it negative or positive?
I think we have not checked that. I think that for the pure fractal lattice, the exponent alpha was like very small, like it should be around 0, and there is a big singularity. So I think that it was difficult to extract the alpha exponent. But yeah, this would definitely be good way of checking the scaling relations if you are able to precisely determine the alpha exponent. And I think that so I'm not sure, but into this scaling relation between alpha, beta, and delta, I think so. There is also there should be also included the dimension.
If I remember correctly, the relation between the alpha, beta, and delta, there is no D, dimension D.
I see. Okay, so yeah, so there is this problem with the big singularity, and it's difficult to actually obtain reliable estimates.
Thank you very much.
Okay, is there any other question? So I have one question about the inverse J1J2 lattice. So in the limit, when J1 equals to 0 or J1 equals to 1 and J2 equals to infinity, probably you can calculate everything just using the scaling relation of a finite clusters consist of J2 lattice only. Have you checked that sort of analytic calculation?
So analytical relation when we are in the inverse fractal regime, if I understood. We actually have not looked into that. That might also be interesting thing to consider. But in the inverse fractal, in its limit when J2 goes to infinity, we would actually get some like very strongly connected these square regions of just square lattice Ising models. Yeah, so not sure like how interesting that would be.
So just regularize the interaction by J2. That limit is like that. J2 equals to 1 and J1 equals to 0. This means that whole lattice structure, whole lattice consists of disconnected block of Ising clusters of J equals to 1. So I suppose those how to say this such an ensemble, the thermal property of such an ensemble can be calculated analytically if one assumes the finite size scaling relation for each clusters that consists of that construct the ensemble. So this is just a comment. So if you have time, please check it.
Yeah, thank you very much.
Is there any other question? Oh, I have one more. So you spoke about the matching condition of the isometry. So when you renormalize perform the renormalization group transformation, you use those isometries created from each environment. But how many types? I suppose you use only 2 types of isometry. Is it correct?
So we use 2 sets for insides of each cluster, and also 2 sets for outsides, like the boundaries.
Is that sufficient? Are those sufficient? I suppose the type of boundary is more than that, no?
Yeah, so like very strictly speaking, there are more types of boundaries, but it's actually sufficient to use like these non-homogeneous and homogeneous as we defined projectors. So like in this example, when we are projecting the upper leg of the second pattern, these projectors are obtained on the very last pattern, so only on this homogeneous structure. And it seems to be numerically fine. Like, yeah, it works well.
Okay, so it works numerically anyway. Okay, I understand.